Hi everybody and welcome back to this short course of bioinorganic chemistry. We have been discussing about our life with dioxygen. Okay, to most important biological reactions, as you all know, one is photosynthesis, another one is respiration. You know, in respiration you need oxygen and which converts to energy, and oxygen carrying proteins are responsible to carry this dioxygen, and as one can see that this oxygen plus 4H plus 4 electron gives rise to 2 molecule of water at a potential of plus 0.815 volt. So, oxygen converts to water, which usually gives lots of energy, and if you give 4 proton 4 electron all at a time, then oxygen converted to water. As I have said earlier that nature also do mistake. If this dioxygen reduced partially even, then it generates lots of intermediate. Those intermediates are harmful. For example, after 1 electron reduction, O2 converts to O2 minus superoxides. Superoxide again after 1 electron reduction converts to peroxide O2 2 minus, and O2 2 minus converts to H2O and OH radical after 1 electron reduction, and OH radical again after reduction converts to water. So, unless you give 4 proton 4 electron all at a time, it invariably produce even if small amount, but some of these intermediate, and these intermediates are highly poisonous in the biological system. They are called biological poison, because they produce uncontrolled reaction. You know that radical reactions are very dangerous, because it is difficult to stop, and these radicals or these species, reduced species, collectively called reactive oxygen species. And aging and age related diseases results from this ROS mediated oxidative damage of lipid proteins and nuclear and mitochondrial DNA molecule. So, since these reactive species are produced even if a small concentration, so nature has a solution for it. Nature has made a solution to get rid of this problem, and this is what the nature designed superoxide dismutase enzyme to destroy the superoxides. As for this reaction, as you can see, superoxides plus 2H plus produces peroxides and dioxygen. So, superoxide basically converts to peroxides and dioxygen, and the enzyme which is responsible for this decomposition is superoxide dismutase. There are two types of superoxide dismutase. One is the heterometal copper zinc superoxide dismutase, and another type is either manganese superoxide dismutase and iron superoxide dismutase, also known in biology. You can see the active site structure of copper zinc superoxide dismutase. You see that there are copper unit which is ligated with 4 histidine molecule and 1 water is coordinated at the 5th position, and zinc is in tetrahedral geometry, and 3 histidine and 1 aspartate is ligated to that. Now, we will see in details in the coming slides. Now, if we look at the superoxides, very interesting. Superoxides actually converts to oxygen and peroxides. 2O2 minus gives rise to O2 plus O2 2 minus. That means, O2 minus converts to O2, this is oxidation process. O2 minus converted to O2 2 minus is a reduction process. The same species undergo oxidation and reduction at the same time. We call it dismutation reaction or disproportionation reaction. And if we look at the thermodynamics of this, the two redox potential, one is O2 minus converting O2 plus electron, it produces E0 of plus 0.33 volt versus normal hydrogen electrode. This is reaction 1. Second reaction, O2 minus is reduced, O2 minus plus E gives rise to O2 2 minus peroxides, where E0 is plus 0.89 volt versus NHE. So, overall reaction is 2O2 minus gives rise to O2 plus O2 2 minus, and if you calculate the overall free energy change delta Z, it is minus 117.73 kilojoule mole inverse, large negative free energy change. That means, the reaction is spontaneous process. That means, this superoxide spontaneously undergo decomposition, giving rise to dioxygen and peroxide spontaneously. This being so, that why did nature design an enzyme called superoxide dismutase to do this decomposition process? So, this is, although it is a spontaneous reaction, as I have shown you that delta Z is large negative and thus spontaneous. So, this will always happen, but nature needs this superoxide to be decomposed as fast as possible, because superoxides are extremely poisonous in the biological system. So, it need to be decomposed almost immediately if it can, and that is the reason why superoxide dismutase enzyme has been designed. Now, how an enzyme actually accelerates this decomposition process? Now, there are two types of mechanism. If the metal is an redox active metal ion, then what would happen? The mechanism 1 is shown with the redox active metal ion, where the metal ion getting oxidized and reduced, and thereby oxidizing and reducing the superoxide also. For example, that in the first reaction, the metal get reduced, whereas superoxide get oxidized to dioxygen. Whereas, in the second reaction, the reduced metal further get oxidized and superoxide get reduced to peroxides. So, same metal getting reduced and oxidized, also forcing the superoxide to oxidize and reduce. Okay. In mechanism 2, the metal ion is non-redox active. So, if that is so, what would happen? In that case, as you can see that Mn plus, so metal oxidation state does not change during these reactions. So, what would happen? Metal and superoxides forms a complex or adduct. This metal superoxide adduct reacts with another superoxides in presence of proton, it converts to peroxides and dioxygen. So, here the beauty over here is that metal ion does not change its oxidation states, rather superoxides converts to oxygen and peroxides, that means oxidation and reduction. In mechanism 1, the metal also getting oxidized and reduced, because metal ion is a redox active metal ion. It has been seen that mechanism 1 is actually inoperational. This being so, what kind of metal is suitable for this purpose? Now, let us see that why did nature choose some metal ion. Now, what is exactly happening in superoxide dismutase? That it is that superoxides, this is there are two couple, one is O2 O2 minus couple, its redox potential is minus 0.33 volt, and another couple is O2 minus to O2 2 minus, and the redox potential is plus 0.89 volt. Thus, any metal which are capable of one electron redox chemistry between M n plus and M n plus 1 state, that has a potential between the limits of minus 0.3 to plus 0.9 volt. Okay. So, any redox active metal ion which have a potential window of minus 0.3 to plus 0.9 volt are in principle capable of doing this dismutation reaction. And there is no surprise that why nature use copper, iron metal ion. As you can see, their redox potential indeed comes in between these two extreme limit of minus 0.3 to plus 0.9 volt. As I have already mentioned that there are basically copper zinc SOD is present, and there are some evidence that iron SOD and manganese SOD also known in the literature. You can see their structure in copper zinc SOD, as I have already said that there are two metals, one is copper center and zinc center, and a water molecule which is ligated at the 5th position is present with copper. In case of iron also there are 3 histidine, 1 aspartate is ligated to the 4th position, and a OH group is ligated the 5th position, which is in iron SOD. In manganese SOD also very similar to iron SOD. If you look at the catalytic conversion Kcat, okay, what you find? You find that for copper zinc SOD rate of catalysis is 2 into 10 to the power 9 mole inverse second inverse. For iron SOD the rate is 3 into 10 to the power 8, for manganese SOD 5.6 into 10 to the power 7. You see that the conversion rate is very high, 10 to the power 9, whereas uncatalyzed reaction is very low, and nature has used this enzyme to speed up this rate of conversion. Copper zinc SOD, what is happening? The proposed mechanism is as follows, that copper goes to the mechanism 1, as I have already told you that copper 2 plus undergo a reduction to copper plus 1, while O2 minus superoxide undergo an oxidation to O2. In the next reaction, this copper 1 again reacts with another molecule of superoxides and converts to is an oxidation. So, copper 1 is getting oxidized to copper 2 plus, while O2 minus is reduced to O2 2 minus. So, superoxide converts to peroxides and copper getting oxidized to copper 2 plus. If you see what is happening, that copper 2 plus converts to copper 1 and copper 1 converts back to copper 2. This kind of shuttling back and forth of copper between two common oxidation states is popularly known as ping pong mechanism, and this has been believed to be happening for copper zinc superoxide dismutase reaction. So, if you look at this copper zinc superoxide dismutase in the resting state, and you see that this copper is in distorted square planar structure in the resting state, whereas zinc is in tetrahedral structure, and the difference between copper and zinc is are more than 6 angstrom in the resting state. Okay. So, this is the X-ray structure of superoxide dismutase. As you can see, there is a huge protein which are wrapping this copper zinc SOD molecule, and you see that if I remove this protein, this copper zinc SOD, which is actually the active site structure I have already shown you, it can be seen where this copper and zinc is bridged through a histidine group. And in order to see that what kind of mechanism is happening in copper zinc SOD case, and you can see that copper ion, which is ligated to a weak axial ligand like water molecule, is replaced in first step by a superoxide O2 minus. Okay. And the superoxide is getting stabilized with a amino acid arginine plus, and this superoxide then undergo oxidation and copper 2 plus undergo reduction simultaneously. So, superoxide converts to oxygen and copper 2 converts to copper 1. Now, once it forms a copper 1, there is no bond between copper and this histidine nitrogen, which was bridging between copper and zinc. Now, this once again binds to another superoxide molecule. This copper 1 is oxidized to copper 2 plus, while superoxide is reduced to peroxides O2 2 minus, and as you can see that these peroxides is very weakly coordinated, and a water molecule immediately replace this peroxides and gives rise to hydrogen peroxides, and water comes back, and this catalytic cycle starts its action once again. So, this is a proposed mechanism how a superoxide getting oxidized and reduced, while the metal copper is getting reduced and oxidized. Okay. And they are helping each other, they are coupled, both the redox process are coupled in such a fashion that the speed up rate of these reactions becomes very, very high. So, the disproportionation of superoxide by redox active metal ions is generally thought to occur in two 1 electron steps, like as I have shown the ping pong mechanism. Copper 2 plus getting reduced to copper 1, while superoxide oxidize to oxygen. Again copper 1 is getting oxidized to copper 2 and superoxide getting reduced to peroxides. So, if you look at this rate constant value, uncatalyzed rate constant is something like 2.5 into 10 to the power 5 mole inverse second inverse at pH 7. While if you use free copper 2 plus ion, the rate is 8 into 10 to the power 9 mole inverse second inverse. And this copper 2, however, the free ion has never been used, because as I have said earlier, the free ion is like a poisonous if it is not good. So, nature never use any free metal ion, rather complex ion they use it. Now, the problem is that once the copper is complexed, then rate of these catalytic reactions getting reduced. Now, question is that how in copper zinc SOD the rate is so high. So, in order to achieve the very high catalytic efficiency, the active site must provide 4 things. 1, a high rate of access of superoxide to the site and rapid release of products, here it is dioxygen. Number 2 is an open or exchangeable coordination position at the metal ion if an inner sphere electron transfer mechanism is involved. Third is rapid protection of the peroxide anion, and fourth is appropriate thermodynamic driving force. And this is what is shown in the design. If you look at the design, very nice design, it is a channel like structure and copper site is clearly the site of primary interactions of superoxides. From the excess structure, it is been shown that copper ion lies at the bottom of the narrow channel that is large enough to admit only water or some small anions or similar small ligands. In the lining of the channel, there are positively charged arginine residue, which are actually gives a direction to the superoxide to reach to copper center. And near the mouth of the channel at the surface of the protein, which is 2 positively charged lysine residue is present, which are believed to play a key role in attracting the anions and grinding them into the channels, so that it can reach to copper ion and then it can be released again after formation of either oxygen or peroxides. So, in this way this dismutation reaction become so fast. So, copper center lying at the bottom of this narrow protein channels and interacts with superoxides and all small anions. And the design is such that only small anions can passes through and reach to copper. No big anions or no other molecules can reach copper center. Okay. Now, we try to understand what is the role of copper and zinc in copper zinc SOD. Whether copper center is important or zinc center is important or both the center is equally important. Now, in order to do that, so this is what is the copper zinc SOD. You can see the protein backbone is shown over here. Now, if one use a strong chelating ligand like EDTA, what would happen? It will immediately remove copper and zinc, and you get a native enzyme without any metal and which is completely inactive molecule. Now, once you put copper to solution into this demethylated species, what would happen? This 2 copper ion is sitting and ligated to the histidine molecule. and it has been found that this dicopper unit also is active towards superoxide dismutase activity. However, they are not thermally very stable. Now, once you put zinc to solution, then one of this copper which is ligated to aspartate group will be replaced by the zinc, and this copper zinc SOD is reproduced. The enzymatic activity is there as well as is thermally very stable. Now, so what does zinc ion do? Zinc is primarily maintaining the structural integrity of this enzyme. Zinc cannot bind superoxides or any anions, and removal of zinc does not significantly diminishes superoxide dismutase activity. Zinc actually provides the thermal stability of the enzyme. Now, what copper center is doing? Copper center is responsible for all this activity. What we have seen, that simultaneous oxidation and reduction of the metal as well as the superoxide. So, this is the site of superoxide binding, is responsible for all this enzymatic activity, and removal of this copper ion completely stop the superoxide dismutase activity, which suggests that copper center is the key catalytic center for copper zinc superoxide dismutase. The great oxidizing power of dioxygen is utilized in respiration to produce huge amount of energy that we enjoy every day. During such respiration process, O2 is fully reduced to water, which would require 4 protons and 4 electrons that need to be added in a concerted manner. However, incomplete reduction of dioxygen produce reactive oxygen species such as superoxide, peroxide and OH radicals, which are extremely poisonous for our body. Aging and age related diseases are result from reactive oxygen species mediated oxidative damage of lipid, protein and nuclear and mitochondrial DNA molecules. I have discussed today how our life is fully protected from such reactive oxygen species. Although dismutation of superoxide is a thermodynamically favorable and also a spontaneous process. However, in order to destroy the extremely harmful superoxide almost immediately, our mother nature has designed such superoxide dismutase enzyme. I have shown here the enzymatic structure, roles of the metal ions involved and also the mechanism of their actions in great details. Although superoxide dismutase decomposes extremely harmful superoxide, it also produces peroxide, which is another harmful product in biology. In my next lecture, I will talk about catalase and peroxidase enzymes, which not only destroy these harmful peroxides, but also utilize them to something extremely useful for us. Thank you.